Welcome to a new test and teardown video. This time we're going to look at this AC/DC power supply. I don't know if you can maybe figure out the size of this, but it is very, very big. 6.2 kilos. I had to put it on my scale. Oh man, it's crazy big. And look at the cables. Okay, they're not nearly as thick as a finger. I got quite small fingers, by the way. Let's look a little bit on the specifications sheet here. Oh, we got some reflections, that's annoying. So the company is called Power Systems Omega. Of course, it's from USA. It's a server power supply. Model number here is MF2-1C-4BDD. And there's a few very interesting things here. So the DC output is 840 watts maximum. But if we look at the different outputs, see there's 12 volt, 12 amps. So that is 144. Then we got a 12 volt 1 amp. So that's another 12 watts. So let's look at the two big beefy outputs. That will be the two super thick cables here. 5 volt, 110 amp. So that is 550 watts, right? And then 3 volt 75 is 247 and a half. Yeah, but if we add all this together, it's 953 and a half. So we are a little bit like 110 watts short. So that means we are not allowed to load all of the outputs at full potential at the same time. That is just a little important thing with multiple outputs, power supplies like this, something to consider. And that will be the tiny little connector for the other one. And there's also a little other connector, probably some feedbacks and stuff like that, adjustable. We got some individual adjustments for the different power supplies. We should definitely try and open this one and have a deeper look what is inside. So there's an extra isolation sheet in here. We got a little controller board. Quite a lot of heat sinks, but that is of course not a big surprise. Current sense. So we got, a lot of current sense is going on here. And that will be the main. So main input is of course well, I think that is not exactly what I think it is. Could be just a filter, but it could also be the power factor inductor. So there's probably a step up, a rectifier, a primary system, and that's most likely the controller board for that. Common mode filter, and we got much more input filters. Input goes directly to that little box with that filter, so that is a really good design. I also like the way the fans go and cool everything and all that. Oh, that will be trigger transformers for the primary. So there's a full bridge there, and there's another full bridge there. Got some more stuff. Yeah, I have to see if I can get it all the way out of the cabinet. So that was quite easy to get out of the cabinet. And there's a reason why I get stuff like this. It's of course because it's blown up for whatever reason. And I get this just to try and see how it's designed and what is fun inside this box and all that. And I already found one good problem. Of course, what you can see is not always the whole truth, but I expect this diode here is exactly the same type as that diode. So there's something in the low output. So this is the 3.3, 75 amp output, and maybe the other output is working, the high current output here. Got some really cute capacitors right there. And also we got those really special capacitors here on the primary side. So that will be high voltage, high speed capacitors. And note the distance. That is to make them high speed, where normally you see the distance here between the two ends. So that is a lower speed capacitors. Yeah. It looks like they put on a little bit bigger capacitor compared to the footprint. This is like a 2020 size footprint, and they found one of those better, obviously. I really like the way the shield is screwed into the chassis and all that. Very good design so far. I want to try and pull it completely apart, because I know that this is completely blown up anyway, so I'm not going to repair this one anyway, so I might as well just see what can we learn from this one. This connector here just fits clickety click, and that will be the fans. I don't see a lot of nasty slimy dirt or anything like that. I mean, this probably blew up quite early in its lifetime. I mean, I don't see a lot of, black parts around where I would have expected parts to be black and brown after running very hot for many years. There isn't really a lot of that, and I don't see any like swollen capacitors or a lot of that. But let's try and dig a little bit deeper into this. See, there's a thermal fuse. What is that? So that is a minimum load resistor to make this output stable. That is a classic problem with high power converters. They need a minimum load to make them good and stable, and then they figure this out and then added a little bit of a I don't know, a little oopsie, I would call that. Got some pretty cool inductors or noise suppressor filters here. Look at the thickness of that wire coming out of this. I think there's a power inductor or some stuff down there. I really love the way they made all this with the screw-on terminals in here as close to the capacitors and filters and everything like that as possible. And this is all there is, to get this super low impedance. And so you want to screw your big fat cables in here, of course. You also want this to be out of the way in your case design and all that. Let's see if I can maybe pull some of these out, because I really want to see what is going on here in the two regulation loops. How are they doing all this? Is it really just this inductor here? I mean, I found some other problems. So here is the high current output, and I mean, look at the capacitors we got here on the output. just a few electrolytics and those ceramics. So if we look at the ceramics, see, they have been overloading those capacitors, so they kind of blew up internally and shorted. I don't know if you can see how they blew up. And they spit out some of their internal guts. So, well, that is of course not so good. I think I figured this out. I really want you guys to see how crazy is this. So this is the secondary for the 5 volt 110 amps, all right? It is normally mounted, well, the other way around, like this, okay? And this, here is the output. I removed 2 capacitors. Those 2 capacitors, they of course leaked as well. And you can imagine that, and then the SMD capacitors on the bottom, which also cracked and leaked and overloaded. But anyway, we got 1 winding for 5 volt. That is it. So this is the negative. Negative goes via this inductor, and then output goes through the 2 capacitors like that, okay? Again, from ground, we got 1 winding to 1 diode, and we got 1 winding the other way around to that other diode. So this diode is delivering half of the current at half of the time. Those 2, right? So that means the sum is 110 amps. So we got 1 screw here, and this 1 screw goes to this capacitor here. So that is a filter. So this filter capacitor is connected to the first point. You see, diode output, and it's not electrically isolated from the heatsink. So that is the first capacitor. Then you have an inductor, just this 1 winding, and that connects to the other part, and then the last capacitor, and then the output. So that is the entire output circuit. And I think I will take this a little bit more apart so we can see the windings here on the primary side of this 550 watt transformer. So this was not a current transformer like I said first, but this is the primary to the secondary. This is a transformer, output transformer. The 2 thin wires here, they go to a full bridge. I don't know how easy that is to see, but those 4 transistors, that's a full bridge FET switch, and that will be trigger transformers for the gates. And we got on the bottom of the circuit board, we got all the driver transistors to drive the primary sides of the trigger transformers. And the reason why you see only 2 here is because this drives 1 set and the other one drives 1 set, and it's a positive and a negative pulse that either activate this or that FET in the full bridge. And that's why you also have a full bridge push-pull here on the, let's see, look at that. All those transistors here drives the 2 trigger transformers, 4 transistors for one, 4 transistors for the other one. So again, a full bridge gate drive system. And we have different turn on and different turn off system here, with a little diode and transistor to handle the gate of that transistor. So this is quite a normal way to do this, really. And then the high frequency loop is compensated here with a good capacitor. Here you see the 2 outputs in the center. That's the ground. See, there is definitely only 1 winding. I'll try to see if I can get these out somehow. Oh, this is... Oh, of course I cannot get this out through the hole, can I? Oh, by the way, in here there's a transistor and a capacitor, so this is a snubber circuit that was connected on top of the output diode. Should probably take out this diode and show you the part number. Maybe it still works. It's really nicely done here with the 3 screws and one, see, like that, so it presses down to that heatsink. I wonder what is the forward voltage of this diode. So it's a dual Schottky diode, CPT20, 130 amps, 20 volts, right? And the 44 watt voltage of each diode, using a little diode tester like this with a very, very low forward current. You should see this. 80 millivolts and 77. Isn't that a little bit impressed? Yeah, I think that's pretty impressive. I'll try and give this a lot of more amps and let's see what it can do. But that is a keeper for some cool projects one day. Try and imagine this is the inductor that holds all the energy in at the time when the diode is not, the transformer is not delivering power. I mean, it stores the energy in this inductor and then it free runs to the next time and to the next time, right? And then, I mean, how can they hold 130, 110 amps? That's, of course they couldn't. Let's do a little paper cat. So this is the 550 watts transformer, just like a little ring, for example. So I counted the windings here. So that is 35 windings on the primary. So I made a little drawing here. So 35 windings. We got 1 and 1, and that's connected. The center point here is connected to the output ground. So that will be our super diode. So since they are phased, so it's like that, right? So there's only one of these two halves that generates power. Then it goes this way. So that means you have 5 volt here, or you have 5 volt here. So if there's 35 to 1, that means if there's 5 volt on one windings, then you have 175 volt in average, so to speak, on the primary side. But also, you need to allow a good regulation distance. So normally you design these for 50% like this. So that means your 175 is now 350. And then 50% duty cycle like this. So this is the AB transistor set. So the A transistors turn on, and then the B transistors turn on in time. And in all the dead time, you have nothing generated from the primary side. And then it is all done here in the loop the rest of the time that delivers the output to a constant output current and voltage, right? So that is how this unit is made in its simple, a simple version of that. So there's another output, and that is the 3.3 volt, 75 watts. And it is very, very much the same, but there are also a lot of important differences. So let's again see the main secondary is again one winding and one winding, and then the two mega diodes here, they're using a little bit different diodes, but it's more or less the same idea, right? And again, I think this is also, maybe a little bit more than 35 windings here on the primaries there. That'll be the gray wires. They go through some current, detect current sense transformers, and again a full bridge for that. But now comes the cool thing. The extra windings we see here, that will be the negative 12 volt and the positive 12 volt. And of course you need more windings, because here is 3 volt for 1 windings. So we got a little bit more windings here to generate the positive and negative 12 volt outputs. And I bet we got some transistors and stuff like that hidden. Yes, we got on that. It's of course impossible to see, but on the other side of this board, we got some transistors and rectifiers and stuff like that for the 12 volt, and they're actually also regulating the 12 volts, and also the positive and the negative 12 volts. They're also individually regulated, and that is done by those extra inductors you see here. So since you now have a voltage that is made to be a little bit too high using those windings, and then you have individual not coupled inductors here, you can pulse those inductors using some transistors and then rectify the outcome of that, and then have individually regulated outputs. So that is also pretty smart done in a very, very compact package. I should probably try and see if I can get in there, but it's not going to be easy. So they just crimped it like that to have a very good connection. And then 1 winding and 1 winding, that's it. So the 12 volt secondary is connect those 2 windings here. There, it looks like we just have 4 wires, but they are connected 2 in parallel and then the other set in series. So that means we have imagine if this is the series center point. So then you have a push, pull, and a center. And this is also how it's done using the negative 12 volt. And the reason why they wind the transformer like this is to be very, very sure they are all perfectly symmetric and exactly the same length and stuff like that. So, and I've taken out everything here so we can easier see. Also, we can see the series connection, the parallel and the series connection, and then the 2 inductors. I don't know if we can see any of that. All the transistors and stuff for that is on the other side, and I'm not sure I'm able to get this thing out. And that's of course all the current sense transformers. And a little thermal protection. So that's a relay that switches off when there's too much heat on the heatsink. So that's a good idea. And the capacitors for the 3.3 volt also leaked all over the place, as you can see here. And there's there's even wet, but there's this really funny smell from these capacitors. So it's always quite clear what's going on. And I think they did exactly the same here with the center. How can I show this? Ooh. See, that will be the 2 diodes. And then we go down here to the first capacitor. And then we have this power inductor to the last capacitor. And there you have it, the output. So of course they overload those capacitors with all this ripple. Oh, another little snubber. So that will be the low voltage rectifier. And what is it called? STPS 12035. So maybe it's 125 volts and then 35 amps per diode. And let's try and check this diode. Is that one still? Yes, it is. So that is good. So that is definitely another Schottky diode with a very low forward voltage drop. And I find, of course, a lot of other blown up. This entire area here completely blown up by this lead capacitor and all that kind of stuff. And this is in this area. Well, let's look at the other side here. So something bad happened right here. Most likely the capacitor just started leaking and all the acids going through the via holes. You can also see this transistor here is blown up. See? Well, current was very, very much too high in that direction. But what I really wanted to show was the inductors here, and then the transistors. No, those are called diodes. Ah, so that will be the double diodes for the 12 volt. And here is a regulator for the 12 volt negative, and that is a something filter, maybe, I don't know. I was super sure they had an extra regulation. It's probably done. Yeah, okay. So here's how it's done. So it's done here. So you're pulsing those. Where are they? Yeah, here we go. Those will be the inductors. So they're probably pulsing them somehow and then measuring the current and all that kind of stuff and creating a little regulator for that. And they probably also use some of this. Oh, this is a 7812. But there's probably some other stuff here regulating the other one. And of course this blew up. Oh, it says here it's from 1990. Can we see that if we go closer? 94. It's not 80, man. Come on, it's got to be 90. I probably need a better camera for this. So that is the age, at least of the circuit board. It looks like some of these components had a really hard life. It's also full of protection diodes, fuses. Did I explain a little bit about the primary? So the input comes in here from that filter. See that big fat track, and there's another one on the other side. And then it goes in this area here where we find rectifier bridge and a little, I don't know exactly why, but I think the rectifier here and this transistor here, and there's probably also one more in there somewhere, the diodes and stuff, together with this, and we got in here a lot more transistors and stuff like this here on the. So this is the power factor, PFC, and this one is handling the incoming AC so that you rectify into those capacitors and you follow the input sine wave. Otherwise, if you didn't do this, there's of course a demand to do it correctly, and but if you didn't do that, you would use all your current at the top of the sine wave, and then your peak current will be very high, and you don't want that. So that is also a reason for doing this. yeah, I think we have seen all there is to see. There's not a lot of surprises in here. A little controller for the power factor, and I think we have seen all there is to say about this fantastic, complicated and also very fascinating power supply, I must say. So I think I will end this video here, and I will try and clean up everything. So thank you very much for watching. I hope you had a little bit of fun, and I hope to see you soon again. Bye bye.